Well, last night we introduced you to a brand new language called logarithms. And the number one thing we walked away last night was with the idea that logarithms are the inverses of exponential functions. And we talked about how to convert a basic equation from logarithmic to exponential and vice versa using our around the world technique. Well, tonight we're going to put 100% of our energy into graphing these logarithms. We're going to take a look at just a couple of big goals here today. We're going to explore our basic log graphs, and what we're going to learn is that 99% of them look almost identical in the sense that they cross the x-axis right here at 1, and they have a vertical asymptote at x equals 0. And those are the two big common traits that our basic log graphs have. Now we're going to move beyond basic, of course, and we're going to flirt with a bunch of transformations. What do transformations mean? Well, those are describing like shifts. We may move it left, right, up, or down, or we may do some reflections. So transformations is a big word that includes both shifts and reflections. May reflect it over the x-axis or the y-axis or something crazy like that. And of course, our last thing here tonight is we're going to study the domain and range of these functions and be able to describe them using both set builder notation and interval notation. So that's kind of a glimpse of where we're heading tonight. So our introduction example here, introductory example, is we're going to graph a log function, log base 3 of x, but before we do so, we're going to work on this exponential function. So I'm going to try to keep my work color-coded tonight. I'm going to do everything with regards to the exponential function in orange. And so they wanted us to substitute a -2 in for x, and 3 to the -2, we could call it 1/9, or we could call it 0.111, yada yada. 3 raised to the -1, we could call it 1/3, or we could call it 0.3 repeating. 3 to the 0 is 1, 3 to the first is 3, and 3 squared is 9. So I'm going to go ahead and graph that one. Now, one of the things I did omit, you'll notice there, is I did not graph the asymptote that should be right at y equals 0, just because when we're doing multiple graphs on the same sheet, it gets a little cluttered, so to speak, and it makes it harder to make the point we're going to try to make later on in this example. But now all I'm going to do for the log graph is I'm going to switch my ordered pairs because of the idea that we're working with inverses here. So I'm just going to say that all of my x and y values are going to flip-flop. I'm going to say 0.111 repeated is my x value and -2 is my y value. 0.333 repeating is x and -1 is y. And then 103192. So you notice, just to emphasize, we're just flip-flopping the x and y values, and let's go graph that. Alright, so just as carefully as I could, I got my points plotted. Make sure that your log graph does not touch the y-axis. It's gonna get really, really close down in here, but you don't want it to actually touch it. And there is going to be, and let's go ahead and put this asymptote in because this is today's theme, is we have a vertical asymptote at x equals 0. Remember, all vertical lines are described with x equals, and that's a vertical asymptote. I'm going to abbreviate that because I'm running out of room. Notice the x-intercept is a 1. It crosses the x-axis right there. And they want us to label these rascals. And again, just practice pronouncing these. It's log base 3 of x, whereas this one was y equals 3 raised to the x. All right, now as far as the domain, let's focus on the exponential function here. The domain extends infinitely to the left and infinitely to the right. So I'm going to say the domain is from -infinity, which is less than x, which is less than positive infinity. Now the range is a little interesting. The range never hits 0 or lower than 0. So I'm going to say all y values greater than 0. All right, let's flip-flop over here to the log graph. Let's say the x values, it never extends any further left than 0. In fact, it doesn't hit 0. So I'm going to say all x values greater than 0, or to the right of 0, you could think of it. And the range, it extends infinitely low and it extends infinitely high, although at a very slow pace. So we're going to say negative infinity is less than y, which is less than positive infinity. And what you'll notice there is that the domain of the exponential became the range of the log, and vice versa. The range of the exponential became the domain of the logarithmic function. All right, a real quick comment that I want to make with regards to a typical exponential function, and again, I notice I said a typical one, is that this function is increasing at an increasing rate. In other words, it's gaining momentum and speed as you move along that curve left to right. However, when you work with a logarithmic graph, it's still increasing, but what we say is the graph is increasing at a decreasing rate. In other words, it's decelerating, although it is still increasing as we move from left to right. So that's kind of just a basic difference in the behavior of these graphs. All right, our second example, we get to use the calculator, and they want us to graph y equals log base 10 of x. Now, that's a very special log. You remember from our last video, we call that the common log, because base 10 is the most common one that we ever use, so we have a special name for it. We just call it the common log function, and a lot of times we don't even write the base 10, we just leave it blank right there, and we automatically assume that it's a 10. We also want to make sure we label the x-intercept, and we're going to state the domain and range. So on my calculator here, real quick, the common log button is on that left-hand column approximately halfway down, just to the left of the 7. So I went to y equals, I typed in log, and then they had an opening parenthesis for me. I typed in x and then closed the parenthesis. Now, the first graph here I came up with was what I call zoom standard or zoom 6. And I wasn't particularly in love with the picture. I thought it was like zoomed out a little too much. It was just really hard for me to appreciate the curvature of the graph right there. So then I did zoom. I went back to the zoom menu, and one of my favorite ones is zoom decimal. It's basically kind of a zoom in type of feature. And so I thought the graph was a little better. We could see the curvature a little bit. The calculator does not do a very good job with the asymptote. That's one of the drawbacks on the calculator. Then the next thing you notice, I went to the table, and when x was a -2, I got error, and when x was -1, I got error, and in fact, even when x was 0, I got error. I didn't start getting good numbers until I got into the positive x values right here, and then I'm going to go ahead and I'm going to graph some of these other numbers the best I can and just continue to scroll down through that list and see what we get. And that's one of the best things about the word sketch is we don't have to be super, super precise. We're just going to kind of get the general flow going. And we do notice that right here, 1, 0 shows us that the x-intercept is a 1. We know that the asymptote is guaranteed. And again, that just supports the idea of all of those errors. And I think we're good to go. We're just going to say the domain is all x values greater than 0, and the range is everything from negative infinity up to positive infinity. All right, I'm going to introduce you to one of our first log properties, and we're going to get into a bunch of them later in the week. But this one's called the change of base rule, and I want you to really emphasize this in your notebook and make it stand out, this change of base rule. And basically, here's how it goes. It says if I give you log base b of x, and again, continue to work on your handwriting, make sure that b is a small little subscript. We're allowed to rewrite this as the log of x divided by the log of b. Now, what you'll notice is I didn't put a subscript on these logs, did I? And the reason is because I'm using a common log, and that's part of the rule that says as I rewrite these are working with base 10s. All right, and of course you don't have to write the 10, that's optional. And so we went from working with base B into base 10s, all right? You can make that little note there. We went from working with base B into base 10. And you're wondering, well, why in the world would I want to do that? And so that's my next question. What's the benefit of the change of base rule? Well, the benefit is that now, the calculator only knows how to do base 10. So you can take all sorts of strange logs and now type them into your calculator. Before, when we were working with log base 2 or log base 3, we weren't capable of plugging it into our calculator. So how would we describe the benefit? Let's say we can rewrite strange log bases and now use the calculator. And that's going to be a huge help. Anytime we get the calculator on our side, that is a huge help. So we're rewriting them in terms of log base 10. So here's a very challenging multiple choice question where they've given us a graph and they want to know which of the four equations over here match up with this graph. And there's a variety of ways to approach this, but this is why I introduced you to the change of base rule. I think it's the most efficient way. So what I'm going to do is I'm going to take this first equation and I'm going to rewrite it up here using the change of base rule. And here's how it would look. I would say the log of the quantity x plus 2 divided by the log of 3, and both of those logs are of course base 10, and then you do have the minus 1 at the end. So we're going to have to be very careful how we type this in the calculator, and let me import a picture of what mine looks like right now. Okay, here it is. Here's what it looks like on my calculator. So I did alpha y equals, which was one of my favorite things, and if you don't have that feature on yours, just make sure you use some extra parentheses to surround your numerator, and then you can divide by your denominator, and you would just have to use those extra parentheses. The other thing I want you to make sure your minus 1 is kind of a standalone number at the end, and it's not included within either of those logs. So, and then what I did is I hit graph, which was still in Zoom decimal for me, and it looked like it pretty much had a chance. It looked like it was pretty darn close to this graph, but what I did is I then went to the table and did some further examination, and I asked myself, is 1 comma 1 on my table, or is negative 1 comma 0 on my table? And they were close, but they weren't exact matches. So what that means is I've successfully eliminated number 1 from being a choice. So then I'm going to just try, let's try number 2 here. I'm going to go down below and I'm going to rewrite it using the change of base rule. I'm going to say log of what? Let's say x minus 3 divided by the log of 2 plus 1. And without this step, we can't plug it into our calculator. So we've got to write it just like that, and then let's go try it. Now again, that graph was not very close for me, so I ended up canceling that one off. Let's see if I can bring in a new color here to make some more room. Now I'm going to grab choice number 3 and practice. The biggest practice is just rewriting these with our new change of base rule. This will be log of the quantity x plus 3 divided by the log of 2 minus 1. And then I can hit graph to take a look at the picture to see if it's even close or it has a chance. And I thought this one was really, really close. So then I went to the table of values. And not only did the graph look really, really close, but the table of values was a perfect match. It had negative 2 comma negative 1 on my table, negative 1, 0, 1, 1. And in fact, it had 5, 2 on there as well. So I'm going to jump on number 3, and I'm going to say this is my winner right here, the winning match. And the big theme that I want you to walk away with is the ability to rewrite these equations using the change of base rule and being able to quickly and efficiently plug them into your calculator. Well, at the very end of our homework the other night, we threw a couple of wild problems at you. We wanted to talk about log base 2 of negative 4, and we asked you to try to explain in your words why this was impossible to solve. And we basically said, well, we could set it equal to x. We're going to go around the world, and 2 raised to the x equals negative 4. But we talked about how that's physically impossible. There's no way that you can raise 2 to a power and get a negative number. It's just impossible. Mathematically impossible. And we also had you entertain this idea. What's the log base 2 of 0? And we said, okay, let's set it equal to something. Let's go around the world again. And 2 raised to the x equals 0. And again, we could do 2 to the 0. We could say 2 to the 0 is equal to 1. But there's nothing that I could use as a power that would equal 0. So again, that's mathematically impossible. So we've discovered 2 real bad inner functions, so to speak. I call whatever's in the parentheses right there, I call it the inner function. And that's a term I'm going to use quite a bit in the remaining part of the video here. So what kind of conclusions can we draw? Well, let's say this. We'll go log base b to keep it really generic, and I'm going to use these parentheses. I'm going to say, okay, whatever's inside these parentheses right here, I call it the inner function. All right? And just for simplicity, we're going to let x represent our inner function. I'm going to say that quantity, whatever's inside your parentheses, has to be positive. All right? In other words, x has to be greater than 0. So when we say the inner function has to be positive. And in other words, it's not allowed to be 0, not allowed to equal 0, and it's not allowed to equal a negative number. Those are the two big no-nos. All right, here's a great example to try. So they want us to determine the domain of this function. In other words, what is x allowed to equal? So here's my inner function right here. The base, whether it's base 2 or base 7 or base 10, has no actual bearing on our answer here. I'm going to take my inner function, and I'm going to say it's got to be positive. In other words, it has to be greater than or equal to 0. And now we're just going to solve this basic inequality. We're going to add the 4 over, and then we're going to divide by 3. And this is my domain right here. X can be any number greater than 4/3. Notice it can't equal 4/3, and it certainly cannot be less than 4/3. Otherwise, we'd get a 0 or a negative number up there, which is a big no-no. All right, here we go, our last example for the night. We've got a real feisty logarithmic function they've given us here with a much bigger inner function than we've seen up to this point. They want me to set up a quadratic inequality that would give me the domain of this function. So again, we're focusing on the domain. And we're going to state our answer in interval notation this time as opposed to set builder notation like we did on the last one. So you're going to have to remind me, and hopefully I don't forget at the end of this problem. So my inner function is everything that's inside the parentheses, and I'm going to instantly set my inner function greater than 0. And that's an automatic move. That's just instantaneous, automatic. And now we're working, this is a great review question. It's a quadratic inequality. And what I'm going to do is I'm going to try to factor it and just solve this equation right here. Notice I said equation just for simplicity right now. And I believe I'm going to go with -5, +2. My roots are 5 and -2. The last time we saw one of these quadratic inequalities on a recent quiz, we absolutely nailed it. We hit a home run right out of the park. So there's my roots. I'm going to use -3 as a test point, and then I'll use 0, and then I'll use 6 as my testing locations. And I'm just plugging, for instance, I'm going to plug that -3 back into the original function. And that's going to give me 9 + 9 - 10, which is certainly true, and that's greater than 0. So I got trues, and then when I plugged in the 0, I got -10, which is not greater than 0, and so forth. So what I've got here is I've got my open circles. I'm shading to the right of 5, and I'm shading to the left of -2. And if I use interval notation, here's what my solution would look like. I would say -∞, -2, unioned with 5 to +∞, and that would be the domain. So what do I want you to, when we walk into class tomorrow, I want you to feel comfortable graphing a basic log. I want to make sure you know where the x-intercept is traditionally located at. Make sure you know where the vertical asymptote is before any of the shifts take place. Let's make sure we know the change of base rule. That is going to show up on a lot of our little quizzes, especially our Monday quiz. And let's make sure that we know the domain of the log graphs. Where we start off, we just set the inner function greater than 0. IF, inner function. All right, good luck tomorrow.